The solar system is home to some fascinating worlds, and not all of them are planets. Some of the most intriguing are the moons orbiting these planets. Often overlooked, these natural satellites hold many secrets, offering critical insights into the formation and evolution of planetary systems. Even the volcanic fury of Jupiter's Io and the icy oceans of Saturn's Enceladus hint at their formations based on their shape, composition, and orbital dynamics. Earth's own moon, for example, narrates a tale of a violent collision with a Mars-sized object, resulting in the moon we see today, a narrative that is now widely accepted and understood. Today, we have a good grasp of how many of the 293 moons formed throughout the solar system. Yet among these celestial bodies, the moons of Mars, Phobos and Deimos, stand out as problematic outliers. They defy our conventional formation theories, presenting a significant challenge, and based on our current understanding of how moons form, these too could be considered impossible. To understand why Phobos and Deimos seem to defy formation theories, we first need to understand what these theories are. As the young planets of the chaotic solar system formed about 4.5 billion years ago, planets such as Jupiter and Saturn were encircled by a swirling disk of gas and dust. Rotating around the planet's equatorial plane, this material began to coalesce, forming the moons we see today, such as Io and Titan. Today, Jupiter, Saturn, Neptune and Uranus have many moons that formed this way, a process known as circumplanetary accretion. These moons display orbital characteristics of near-perfect circular orbits that are along the planet's equatorial plane, a sure sign the moon formed around the planet. But whilst these characteristics make these moons stand out, it becomes obvious when others do the opposite, with elliptical, inclined and retrograde motions. Take Neptune's moon Triton and Saturn's moon Phoebe. These two moons are highly inclined to the equatorial plane at 157 degrees and 175 degrees respectively. Both have retrograde motions orbiting the planet in reverse to the planet's rotation, indicating the circumplanetary accretion could not have formed these moons with these orbital characteristics. This suggests their formation origins were far from their host planets, a case strengthened by their unusual densities and compositions. Lightly plucked from the Kuiper belt by the gravitational pull of their host planets, these moons stand out for their orbital oddities, which contrast with the orderliness formed through accretion. At some point in Earth's early history, a Mars-sized object named Theia smashed into it, sending debris from Earth's surface into space, mixing with the remains of the impacting object from which our moon formed. This cataclysmic event is known as the giant impact hypothesis. Giant impact moons each share a chemical signature similar to the parent planet, indicating their formation came from these violent origins. It is within one of these three formation types that Phobos and Deimos should fall, but amongst these well understood processes their origins are proving impossibly elusive. Discovered in 1877 by Asaph Hall, their peculiarities have confounded scientists from the start. Unlike the large moons formed through circumplanetary accretion, Phobos and Deimos are tiny, only about 22 and 12 kilometers across, with irregular, lumpy shapes that are at odds with the spherical shapes most other moons exhibit, suggesting different formation origins. Currently, the leading origin theory for these two moons is the capture theory, suggesting Mars gravity caught either asteroids from the outer asteroid belt or Trojan asteroids near Jupiter. But why is there uncertainty about the theory? Phobos and Deimos have irregular shapes which are at odds with the spherical shape of other moons. Coupling this with a composition similar to certain carbon-rich asteroids known as D-type asteroids, found in the outer asteroid belt and Jupiter's Trojan asteroids, gives us strong evidence in support that these are captured objects. But do these characteristics fit all characteristics of captured asteroids? There is evidence undermining it, as both Phobos and Deimos have near-perfect circular orbits, aligned to the equatorial plane of Mars, when we should be seeing, for captured moons, orbits that are highly inclined, just like those of Triton and Phoebe. It's as if these two moons don't want to reveal their true origin, but a recent study has put forth a provocative theory that may well resolve the issue. Are they the remnants of a comet torn apart by Mars' gravitational pull? Using high-resolution images from the Mars Express spacecraft, which has been closely examining Phobos since 2003, scientists have compared its surface features with various solar system objects, such as Ceres, asteroid Steins and Lutetia, Kuiper Belt objects Arakoth, and Comet 67P. Surprisingly, Phobos' photometric properties closely resemble those of Comet 67P, a bizarre twin-lobed body explored by NASA's Rosetta and Philae spacecraft. The theory suggests Phobos and Deimos may have originated from a single comet that split into two nuclei, or is a comet similar to 67P that was gradually ripped apart when it ventured too close to Mars's gravitational field. Through tidal interactions of the disk debris over time, it formed the moons with their circular orbit along the equatorial plane of Mars. It's a theory that reconciles the conflicts between the capture hypothesis and circumplanetary accretion. But the only way it will be resolved is by collecting samples from these moons, which is exactly what the Japanese Aerospace Exploration Agency is gearing up to do with its Martian Moons exploration mission, scheduled for launch in 2026.